figure I've shared this afternoon. And by much, the transit's the biggest, but 94% of all the discoveries are made with the transit method and the radial velocity method. So they're the big two. You might by a factor of 1 in 10,000. So you imagine a star and just a 10,000th of a drop in brightness. That's what the Kepler, which we're talking about, the Kepler telescope can pick up from there. And a very things. And someone said to you, there's a beetle walking across one of them. Can you tell which one it is and tell information about that beetle? But here's the catch. You're not even sitting in a seat in Mount Eden Stadium to be watching that. You're actually sitting at Cape Town in Wellington, trying to see a beetle walk across at Eden Park, walk across the bright. So something hugely intensely bright with the most subtle of dips, as in 1 in 10,000, from such a huge distance away. That's the sort of science you're talking about. They get a lot of valuable information. So first of all, the size of the dip. So this is what they call a light curve. So it's how the brightness of the light. So you've got brightness up here and you've got a time factor along here. Of course, that's all variable depending on the circumstances. Here you've got your planet going away from the not in line with the star currently. So the light brightness of the star is here, and you get that dip. And of course, you've heard what I've said, so you get the natural thing that this is a huge exaggeration, but it's to illustrate the point. And the star goes along here, the planet rather, and then it goes out beyond our line of sight again, in terms of in line with the exoplanet, and you see the brightness pick up again. So that's called a light curve. And that's called the transit method because you're observing and measuring the difference that a planet does when it goes across in line with its host star. And the time, so there's even more information. So that obviously gives you information about that. Not only they can detect that tiny amount of dip, they can tell you exactly how tiny that little dip is. And from there, they will estimate the size of the exoplanet. And of course, if you measure how long it takes between each little dip, that gives you information on how long it takes for that exoplanet to go round its star. So it's orbital period. And for the orbital period is very simple equations just to work out the actual distance between the planet and its host star. And of course, once you know those sort of figures, you can actually get an idea whether it's in the habitable zone. The habitable zone around a star is the distance whereby the temperature is just right. If that exoplanet has an atmosphere, if it can, it will support liquid water on its surface. Too cold, further out, it'll be that water surface will be ice. Too hot in, that surface water will evaporate and become vapor. So that's what they call the habitable zone. So you can immediately get an idea, just the time between dips, how far it away is from the host cell and whether it's getting your interest more in looking for light. So go back over the video, we talk more all about that. We talk about all the different types of dips and different shapes and so on and timing of them. Okay, so this is, I just put here, this is a star here, it's just a little video that I put together here, and I think I have to do this manually. No, here it is. So there's a star, just fucking, that's what the telescope observes, but it's 1 in 10,000 dip. And check this out, as you'll see, the Kepler telescope looks simultaneously with looking at 150,000 different stars simultaneously for one of them, or two of them, or three of them to be blinking. There it is here, and you can see that's what's going on, what's happening. The exoplanet going around its host star, and you see the light curve dipping. And there it is there. That's what it's looking for. I get my little good dot. Except it's doing that. It's 150,000 stars simultaneously looking for dips for a factor of 1 in 10,000. That's what Kepler, it's just mind-blowing. So these are the two big ones that do the transit. Kepler Space Telescope that's now being retired, and the TESS, the Transiting Exoplanet Survey Satellite, which is still going, and we'll have a look into these now. So that was operational from 2009 through to 2018, and its main purpose was just to look at just one part of the sky and determine if there are exoplanets out there and how common they are in the galaxy. That was its sole purpose. Needless to say, it was highly successful in answering that question, and it observed 530,000 stars. Initially, that one patch, which it was designed to do, its primary mission, 150,000 stars simultaneously. What happened then, it had problems with the gyroscope, and they realised they couldn't keep it fixed on one spot, so they then let it do more wider sweeps of the night sky, called its K2 mission. But the result was over 2,700 confirmed exoplanets discovered. Now, it discovered heaps of them, thousands of them, but there's a difference between that and confirmed. To have an exoplanet confirmed, you must have that discovery also by another method, whether it be the transit, then by the transit method, then by the radial velocity or direct imaging or so on. But you've got to have it confirmed with another independent form of detecting exoplanets to have it confirmed. So out of all its discoveries, 2,700 exoplanets were discovered in its lifetime. So that's pretty incredible. There it is there, the sensitivity. So that 1 in 10,000, or 0.01%, the star's brightness, that enabled it to detect Earth-sized planets, so usually which are rocky, size of our Earth or thereabouts, transiting sun-like stars. And when they say sun-like stars, we're going to be talking shortly about stars come in a wide range of sizes and temperatures. And when they say sun-like stars, they mean stars, host stars, that are very similar size and very similar surface temperature of our sun. So it is able to be able to detect the Earth-sized planets around those type of suns. You need a sensitivity of 1 in 10,000, which the Kepler was certainly able to do. It ran out of fuel and then was retired. So here's just a little 3-minute video. This is quite cool, just to wake you up, but also just to go over. It's quite cool.
NASA's Kepler Space Telescope was the most productive planetary instrument ever built. Of those 3,700 unique planets the telescope watched, Kepler turned up 2,340 results. Kepler was launched back in March 2009 and began operations on May 12, 2009. Kepler was placed into an Earth-trailing orbit around the Sun with a period of 372.5 days. With a longer year, the telescope slowly drifts behind Earth by about 25 million kilometers per year. It uses 1.4 meters finer mirrors to observe a 12-degree region of the sky. For comparison, the moon can have about half a degree, so a region contains hundreds of times the size of the moon. As I mentioned earlier, Kepler was designed to use the transit technique, searching for planets passing in front of the stars in very specific regions of the sky. While previous exoplanet surveys had only found the more massive planets, Kepler was sensitive enough to see worlds with half the mass of Earth orbiting other stars. And everything was going great until July 14, 2012, when one of the spacecraft's 4 reaction windows failed. These gyroscopes that allow the spacecraft to change orientation without propelling. The problem, Kepler was designed to only use 3. Then a second reaction window failed on May 11, 2013, bringing an end to the mission. What the Kepler engineers came up with is one of the most ingenious spacecraft rescues in the history of spacecraft. They realized that they could use light pressure from the sun to perfectly stabilize the telescope and be pointed at a region of the sky. This allowed Kepler to keep working, observing even larger portions of the sky, but it orbited around the sun would only let it watch one region for a shorter period of time. Instead of scanning sun-like stars, Kepler focused attention on red dwarf stars, which can have Earth-sized worlds orbiting them every few days. This was known as the K2 And during this time, it turned up an additional 307 confirmed and 480 unconfirmed planets. The Kepler is running out of time now. About a month ago, NASA announced that Kepler's almost at speed. It was important because one important maneuver it needs to make is to point itself back at Earth and upload all the data to that. NASA figures that it's just a few months away now. When it happens, they'll instruct the telescope to point at Earth for one last time, transmit the final data, and then shut down forever.
Yeah, there you go. Amazing bit of technology, isn't it? Okay, now then there's TESS. That became operational in 2018, still going strong. And instead of being designed to look at one particular patch of the sky to see how common exoplanets are, it's doing an all-sky survey. It's in orbit, all-sky survey of the stars reasonably close to Earth. And it does that every 2 years. And it's focusing, which we'll talk more about later, those particular classes, we'll talk about them, dwarfs like sun-like stars. The bottom line is stars similar to our sun and those cooler than our sun. As of July this year, it had confirmed 638 new exoplanets confirmed. That means discovered and confirmed with another method. But there's such a backlog, it's discovering them much quicker than they can confirm them. So there's over 7,000 yet to be confirmed. That was as of March this year. So you can see they're getting more and more data quicker than they can actually confirm. Very productive. Sensitivity, it could measure a star's, changing a star's brightness as small as about 1 in 20,000. So about, so 2 in 10,000. So 0.02%. Why? Because it's looking at planets, exoplanets and star systems a lot closer to Earth. It doesn't have to be as accurate or as capable as the Kepler. But it is capable of detecting planets down to about 0.8 the size of Earth, 80% the size of Earth, transiting red dwarfs. The smaller a host star is, of course, the easier it is to notice a quick dip in its brightness because it's a bigger percentage. So, but still, it can do 0.02, so it's a factor of 2 in 10,000. Pretty amazing. And I've just got the video for here too, just to give you a taste of the technology.
In the last few decades, we have found thousands of worlds around other stars. A new NASA astrophysics mission will help us find many more. TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. The team led out of MIT has going to find thousands of new planets orbiting nearby stars. And it's going to build upon the legacy of the Kepler mission. Only it's going to focus on nearby bright stars that have sprinkled across the sky, and it's going to help us answer a really important question, and that is, people on the outside of the Earth have planets. During its 2-year survey, TESS will look for signs of planets ranging from Earth-size to giants larger than Jupiter. TESS will search for these new worlds, or exoplanets, using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TESS can detect those subtle dips and even use them to determine some basic features of the planets, such as their size and orbit. Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a vertical strip of the sky called an observation sector.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also the ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will include essentially all the bright nearby stars.
TESS will watch each observation sector for about 27 days, before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky. This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS will fly in a highly elliptical orbit that maximizes the amount of sky the spacecraft can image. and is carefully timed with the orbit of the moon. It will spend most of each 13.7-day orbit collecting data, and then, as it passes closer to Earth, it will transmit that data to the ground. Because Tesla's observation sectors overlap, it will have an area near the pole under constant observation. This region is easily monitored by the James Webb Space Telescope, which allows the two missions to work together to first find and then carefully study exoplanets. Since most of the exoplanets found by TESS will orbit bright stars, missions like Webb will be able to measure the spectra of starlight absorbed by the planet's atmosphere, which can indicate what they're made of. Ground-based measurements of the TESS exoplanets can determine their masses. Combining the masses with TESS's size measurements reveals density, allowing scientists to better understand the exoplanet's composition.
The thing that we're really excited about with TESS is the way that it'll actually build on the momentum that we started with Tesla. So TESS is going to take that same search approach but apply it to the vast majority of the sky, which still hasn't really been looked at in detail when looking for exoplanets. And by focusing especially on planets that orbit bright nearby stars, TESS allows us to start looking at exoplanet composition, atmospheric makeup. And that'll then be crucial when we want to start looking around stars that are either further away in deeper parts of the galaxy as well.
TESS is the vanguard of a new era of exoplanet study and will forever expand our understanding of worlds beyond our own.
There you go. And there's going to be more of these type of things coming out with time as well. It's just mind-blowing technology. And I think one of the things that she touched upon there is different telescopes provide different information, so they can nicely build a picture up. So go and have a look, if you're interested in that, go and have a look at the video from that we did earlier in the year. So these are some of the big numbers. As of 30th of October, over 6,000 confirmed exoplanets, but in 4,500 planetary systems, implying over 1,000 of the exoplanets that they've found are actually part of multi-planet systems, in other words, solar systems. Over 1,000 of those. So that's like one in six are part of a solar system. Someone once asked me too, they said, but that transit method is the most popular, yeah, but it picks up exoplanets going in front of a star, yep, but that's only from our perspective, isn't it? So that's we have to be properly aligned. Yep, exactly. And their point being, which I said exactly, is, well, gosh, all the other stars out there and orientation of planets and stuff, we're just sampling a relatively small amount that's available to us through this method, and look at the numbers they're finding. So, you know, exoplanets are everywhere. Thank you. Okay, let's look at the search for extraterrestrial life. When we look at these planets, what sort of things we talked about, what sort of things we're going to be looking for if we're going to be searching for life. And here's some questions here. So this carries on from our talk about host stars. What is the ideal, I'll go through them all and then give you a few moments to think about it, and then we can go through the right one and why it's the right one. What is the ideal host star of an exoplanet to support life? What's that star's most likely going to be? Is it going to be A, red giant? B, will it be an exoplanet going around a white dwarf? C, going around an M-class red dwarf? D, will it be a G or K-class main sequence? We're going to be talking all about what that means. Or will it be an A or a B class main sequence? So, I'll give you a few minutes to think about that. And the answer was a G or a K class main sequence star, which we'll talk about. So, who got that right? And then who got that right who didn't get a chocolate last time? wound out. And the problem with those, that is the last 10% of their lifespan, but they're relatively unstable state, as opposed to relevant in relation to, say, the main sequence. So, and put that red box around there, is you're going to be looking for a main sequence star. Now, anything's possible out there, but life is a numbers game at the end of the day. You want numbers stacked up. You only got X amount of time, X amount of instruments, so you want to go where the money is. So the money is going to be around main sequence stars. Not to say they might be going around one of those, but that's where you're going to have a look at with your limited resources, a main sequence stars. Now, we've talked about this during the talk during the year, but other years as well, so just this is good revision. So main sequence stars, in that first 90% of their life, come in quite a range of size and temperatures, from really small and dim here, the M and Ks, right through to the O and Bs over there, which are large, hot and bright. And these ones are very small and cool, large and bright. You might say, that's a funny alphabet, isn't it? Last time I went to school, it was A, B, C, D, and so on. It's for historical reasons to do with spectroscopy and so on. And then they were labelled A, B, C, and then they later discovered that actually doesn't relate very well to what's going on in the stars. But they reshuffled things around, but just kept the assigned letters for each one. So that's a little bit about main sequence stars, the range of them there. Our sun is there. It's a G-class main sequence star. We have a surface temperature of about 5,800 degrees. So that's us there. Now, these FABO stars are very short-lived. Why are they short-lived? And the bottom line is that what drives that nuclear fusion in the core of a star is its huge mass of gravity pushing it inwards. Creates those high temperatures and pressures in the core, which drive the nuclear fusion. So it follows that the bigger star is, the more matter, the more stuff that is there that's coming down with gravity, the bigger the gravitational forces, so the higher pressures and the higher temperatures you've got at the core, so that nuclear fusion rate occurs much faster, so it burns through its fuel a lot quicker. So the larger a star, the hotter it is, the higher temperatures and pressures, just because of gravity going on in its core, so it burns through its nuclear fusion rate a lot quicker. So they tend to be very short-lived. The bigger they are, the shorter they live. The bigger they are, the more high energy, because the hottest, they have high energy radiation. As I mentioned, radiation, harmful to life and harmful to an atmosphere. And the other thing is they're very rare. Nature has a bias for lots of small things and fewer larger things, like a bit of a pyramid, if you will, whereby the F, A and B, O classes represent less than 5% of main sequence stars that are out there. Less than 5%. So they're very rare, they're very short-lived, high energy. So once again, hey, good luck to you. You might find one of those perhaps hosting some exoplanets, but you're less likely to. And if you're looking in particular for life, Earth 2.0, you're better looking at something else in terms of limited time, limited resources, and so on. Now, your M class, so MKs are called red dwarfs. In particular, the M class, the most coolest and smallest of those stars, very long-lived. Once again, they're a lot smaller, so they're less matter pulling in through gravity. So the temperatures and pressures at the core are sufficient to have nuclear fusion going on, hydrogen getting rammed together to form helium, to be by definition a star. And once again, with that bias, the M-class red dwarfs represent 75% of all main sequence stars that are out there. So they're really, really common as. But because, and I won't go into this now, but because of their internal structure and the way they do their heat transfer and stuff, they just have from core to surface just non-stop convection, like a boiling jug, just hot material rising to the surface, cooling off and then sinking back down again. And you've got all this going on and that churns things up. So they give rise to very frequent, intense, what they call super flares. So frequently M-dwarf stars, they're called flare stars for that reason, that they'll frequently just give out bursts of high intense radiation and solar flares. So once again, life possible, but it faces some real challenges. Now there's something else going on with these M-dwarfs. Because they're smaller, and remember we talked about that habitable zone, the right distance from its host star, whereby if it's got an atmosphere, the temperature is just right to support surface liquid water. So it follows that if you've got a cooler star, that habitable zone, also known as the Goldilocks zone, is going to be a lot closer. If you've got a massive big star that's so really hot, blazing out really hot temperatures, that habitable zone is going to be much further out. So with these M dwarfs, to get that right temperature, to have surface liquid water, should it have an atmosphere to support that, that habitable zone is really nice, is right in very close. And what does that mean? Two things. One is it's more vulnerable to those high radiation, those big flares that these M dwarfs are famous for. It's going to be more vulnerable to strip that atmosphere away and to damage life. But also a thing called tidal locking would go on. Tidal locking is where you get two astronomical bodies. Classic example is the Earth and the Moon. And in particular, it happens to the smaller one first. Frictional forces, as it goes around, starts slowing its rotation rate down, whereby the smaller object will, particularly a moon around an Earth, or in this case a planet around a host star, if it's close enough and the gravitational forces are big enough, the rotation rate of that planet going around that host star will be exactly the same rate at which it's rotating its orbit. And that's what happened with our moon. You know, we always see the same side all the time. That's called tidal locking, or synchronous rotation. And it's whereby the moon rotates at exactly the same rate at which it's rotating, or orbiting rather, around Earth. So that's called tidal locking. So, which means that these exoplanets, if they've got an atmosphere and they've got surface liquid water, if they're in that habitable zone, they're going to be really close, they're going to be vulnerable to high dose radiation, but also they're going to be totally locked. And that means that one side's permanently facing that star, one side's permanently in sunlight and heat, getting blasted with radiation, and the other side's constantly just looking out to the colder space. Now, that's not to say that computer models suggest that life can get around that if you have a thick enough atmosphere and some movement of the atmosphere and so on, you know, distributing temperatures. Computer models suggest, yeah, it is possible, but jeepers, it's got some real challenges. Life has got some real challenges. So as common as M dwarfs are in a lot of papers, if you have a look at these exoplanets they're looking at, but yeah, they're going to be looking at some M dwarfs because they're just so common out there. But arguably, that's not where your money should be. Your money should be in your K and Gs. These are ideal. They've got lifespans are about 10 to billion years, so that's a good amount of time for life. Our sun lifespan of about 12 billion years. And they represent 20% of main sequence stars. So not a huge number, but you know, 1 in 5, that's pretty good. So they're just in that sort of nice sort of position there. Their energy outputs, like our sun, is relatively stable, and the habitable zones are just in that conducive to life. They're not too far out, they're not too close in, they're just about right. Hence our sun's a G class. That's why we're here, because we are going around a G class. So your G and K class main sequence stars are your most likely, is where your money's going to be if you're looking for an exoplanet that's got conditions for life. Okay. How about then we carrying on from that theme, looking at life elsewhere outside from Earth, extraterrestrial life. We then talked about NASA's Clipper mission to Europa, whereby the search was for the conditions of life, not life. It's not designed, so it's a probe that's heading out to Europa now. It's not designed to look for life. It's just designed to look for the conditions of life on Europa. And Europa is a moon, as we talked about, is a moon of Jupiter, known as one of its Galilean moons. It's one of its 4 relatively big round moons, relatively close to Jupiter. So why are they interested in it and stuff? And there's a lot of evidence. Once again, we talked about all the lines of evidence. There's about a dozen really key lines of evidence that really points to this underneath its icy surface. There's these big subsurface oceans, global oceans, with these big thermal vents going on down here. So to give you an idea, the surface ice on Europa is estimated to be about 22 kilometres thick, considering the thickest ice sheets at the poles on Earth about 5 kilometres. Oh, to give you an idea of the size of Europa, it's roughly compatible. I think it's slightly bigger than our moon, but it's comparable with the size of our moon. To give you an idea of the size, it's got a big thick ice, about 22 kilometres, and its subsurface ocean goes up to about 150, estimated to be about 150 kilometres deep. When you think of the deepest oceans on Earth, go down to about 10 kilometres. someone once said to me, just bailed me up after talking, they said, how did the water get on Earth? And we briefly talked about, without going into it, comets and asteroids, plus a lot came up from minerals. And they said, really? But there's a lot of water on Earth. I said two things. One is, there's a lot of comets and asteroids out there too. But the second thing is, put it in comparison to this. There's estimated to be up to perhaps 2 or 3 times on this Earth yay big, Europa yay big. Europa has over 2 or 3 times the amount of water on it than Earth has got. So you put it into perspective. So there's a lot of water up there. There's a lot of evidence. Once again, go back over the video if you wish. The evidence why, but there's a lot of evidence that on the base of these oceans here, there's these hydrothermal vents with hot water rising up here, full of minerals and stuff, so energy and minerals to support life. So here's the question: what are the essential conditions for life? Either liquid, so we'll go through them and then we'll give the right one. So liquid water and energy. B, liquid water, compounds and chemistry. C, compounds and chemistry and energy. Or D, all three. Or E, ice cream, chocolate and fine wine, as any birthday boy should be enjoying. So the answer is, so who got it? Yeah, is all three. So who got that right who hasn't had a chocolate? Down the back there, yay. Sorry, what's that? That's what I will be indulging with when I get home. And this fellow here got one because it's your dad-in-law, isn't it? Yeah, your father. Yeah. Anyone else? Did I see one? Yeah. There'll be loads of opportunities to have lots of chocolates. Oh, yeah, they're down the back there. Yeah. There we go, sir. Oh, yeah. Oh, yeah. There you go. No shortage of chocolates. Okay. So, yeah, all three. So let's look at the conditions that you require for life. There are 3 essential conditions that life as we know it requires. One is you need a solvent. And there's a huge, that was the talk too. I talked a bit about why it's most likely to be water. The most, as a solvent. You need a solvent to dissolve nutrients into the body of life, to transport those nutrients around the body of life. You need it for its metabolism. Metabolism is where you, a series of chemical reactions to generate energy to help construct and maintain cells and for reproduction and so on. So you need it for metabolism and you need it to get rid of waste. Most likely it's going to be water. The list is long as your arm, the reasons why. People say, oh, have it such and such, have it such and such. And it's going to be water. Water for starters, H2O. The two, just notwithstanding helium that doesn't react with anything, it's the 2 most commonest elements in the universe. It's pH neutral, so it's not acidic, it's not going to do any harm to cell membranes. It's bipolar, the shape of it. It's got a positive and negative charges to the shape of its molecule, which means it dissolves molecules. Once again, the list of compounds that water dissolves compared to this huge, and these other little ones, ammonia and the likes here, and sulfuric acid, the list that they can dissolve are tiny. Water can dissolve. So water is neutral, it's more common, it's going to dissolve things a lot easier. It's got this wonderful property, as we've showed here, down here, because of its structure. If it gets really cold, its solid version of it, state of it, is actually lighter than its liquid. So you get this lovely insulation of ice above it. Imagine if it was the other way around, and you had ice from the bottom. As it got colder and colder, you get all ice and you'd have no liquid water. So water has got many wonderful properties, and almost certainly is going to be the solvent for life as we know it, as we define it. Compounds and chemistry. You need compounds and chemistry to make and assemble the building blocks of life. And we talked about those proteins, lipids, nucleic acids, and so you need those, and of course the big one is proteins, to build and assemble all your chemicals to create your building blocks of life that form the structures of life, the enzymes, the chemical reactions, so on. You need compounds and chemistry, and you need energy, whether it be in the form of heat or photosynthesis. You need energy to drive those chemical reactions to build things in metabolic reactions. So these are your 3 requirements. Europa may have these conditions. There's a lot of strong evidence for that, which, once again, go back over the video if you want, which raises the question, can and does it support life? Sorry, what was that? How has that got energy? What's the question, sorry? Oh, I'm coming to that shortly, yeah. So it has energy, it has heat rising up through those hydrothermal vents. And one of the questions is, where is it getting its energy from? So good question, very good question. We're going to be talking about that, yeah. So that's a good question. Where does it get its energy from? We're going to talk about that. In fact, we're talking about it now. Here you go. What powers Europa's geothermal activity? Radioactivity, B, the heat from the sun, C, tidal locking with Jupiter, D, orbital resonance with other moons, and E, C, and D. And this, actually, you could argue a little bit about, but okay, and the answer is C and D, and I should go through these. So who's got that right now? Hasn't had a chocolate so far? Alex. You'll have a chocolate. There you go. Oh, you have it. Anyone else? Yeah, there you go. Right, Trevor. Way down the back, there's arms swaying and all. Oh, Niven. I think we followed you in just tonight on the
Yeah.
Here.
You didn't follow me to Burger King, mate.
No, we figured you had gone in because we thought you don't need petrol. You've gone to Burger King. Anyone down here? Oh, yep. Whoa. There we go. Okay, guys. So let's talk radioactivity. That refers to when radioactive elements like thorium, potassium, uranium, and so on that just quietly give away, that are unstable. They're just quietly giving away radioactivity. And there is a little bit of radioactivity, but not a lot. But there is a little bit of radioactivity. So if you put A, I'll give you half a point. Heat from the sun, and I think that's what you're alluding to. It's so far out, and it is. It's so far out. Where's it getting that heat from? So far out where it's chilly cold around Jupiter. But we'll talk about it. Tidal locking with Jupiter and the orbital resonance with the other moons is the two. And let's look into that further. So, that's just a nice sort of picture of the artist's impression here. So this is the surface of Europa. It's got this ice layer here up to 5 kilometres thick. 22 kilometres thick, and then there's up to 150 kilometres deep of ocean. And then it's, with its mantle down to its core, it's really hot in there. And that's driving the energy for the hydrothermal events. And here it is here. It's shown there. So let's have a look. What powers these tidal and geological processes? Now let's have a look. It's those two there. So first of all, tidal locking with Jupiter. So Jupiter, as you're probably aware, is the largest planet in the solar system. It's many times bigger than Earth, about 113 times the size of diameter-wise of Earth. And it's got these 4 Galileo moons. A lot of heat inside, it's just getting pulled and stretched. And a good analogy is a paperclip, but a cold metal paperclip. You get a paperclip and bend it backwards and forwards, backwards and forwards, backwards and forwards. Soon gets hot, doesn't it? You can touch it, it gets hot. Same principle, the inside of these planets get quite hot because of the tidal tugging and pulling on them from Jupiter.
But if it's always facing Jupiter.
Yes, but it is rotating, but it's rotating, so it's not like just going around like that, it's rotating as it goes around like that. So it is moving. Now what you have done, you raise a really interesting point here, because, and probably what you're alluding to, that creates huge tidal forces which in turn creates internal heat. But what Tony's probably saying here, well, hang on a minute, wouldn't that soon, that sort of, that would lose its effectiveness with time, and it would. But what maintains those tidal forces, what are called orbital resonances, whereby the moons are relatively close to one another, the three inner moons, Callisto's out of the one for this bit far away, but these three here, Io, Europa and Ganymede, are relatively close, whereby they have gravitational influences on one. So if one's starting to, the closer one, what drives an orbit? Gravity is the force that drives an orbit. So it follows that an inner object orbiting is going to be going a lot faster around an object than the next one out, and so on and so on. So Io, the close one here, goes relatively fast, but as it's overtaking another one, the gravitational forces between the two pull, you pull the slower one back. And if this one gets going fast around here in relation to that one, it pulls it back. So they're constantly pulling each other on a regular basis, whereby they line up on a regular basis in their orbits. And this is it here. So I've got a little video, a little GIF file coming off it. But okay, so here's Jupiter in the middle. Here's Io, there's Europa, and there's Ganymede. And see, Io does one complete orbit, so it's back up here again. And look at Europa, it's only done half. And Ganymede's only done a quarter. Okay, 2 orbits later, Io's back to its original spot, and Europa's gone a complete way around. Ganymede has just done a half orbit. 4 orbits of Io, the back all lined up again. So that's called orbital resonance. So they regularly line up, and that's because of all the gravitational influence they have on one another. And here is my little, here it is here. And I'll tell you the significance of that in a minute. So here it is here. So they're all lined up there. Around. Then there's 2 of them lined up. All lined up again. So that's called an orbital resonance, whereby on a regular basis they're constantly tugging on each other. You might say, yeah, okay, I get that. And it's that repeated, if something is just going around its planet, Jupiter, if it's had its sole way about life, it would have, if say it had one moon, for example, that would be going around in a fairly circular orbit. But because you've got these other moons further out and they're all in this orbital resonance, they're trying to, but tug of war with Jupiter, they are trying to make those orbits a little bit elliptical, a little bit oval-shaped orbits. And because of that and the constant tugging, that tidal bulge and the way it's facing Jupiter is also changing the whole time as well. And that's why that tidal locking and heat generation, because of the stretching and compression and so on that's going on internally, keeps going billion after billion after billion years. It's because of the resonance that's going on. And here's one little paperclip thing there. So that's what's driving those geological activity. And of course, you might argue, well, the closer you are to Jupiter, the more geothermal activity you're going to have stuff going on. Absolutely. Io, that inner Galilean moon of Jupiter, is the most volcanically active body on the solar system. Then Europa has got these hydrothermal vents, and Ganymede's got some evidence for some of it. So that's the Europa. Then we talked about the Vera Rubin Observatory. It's pretty cool. And it's using it's got a very special function. It's got a 3-mirror design, and that's designed to allow it to do some wide field surveys of the night sky with minimal aberrations and with high resolution. And I think I've got a little video here. It's very unique, large, unique mirror configuration. This is another little GIF file here. Might need to do it manually, that's fine. Try it. Okay, that's cool. I'll just try manually.
What? Yeah.
It's working.
Oh,
Right.
no. Can you try pressing this? It just went out straight away. Nope. I guess not.
That's all right. We won't worry about it. Okay, so I can do it. Yes, this one's got a nice diagram with some arrows here. So the light comes into the telescope. That's these little arrows here. They go down. They hit the primary mirror here. They then get reflected back up to the secondary mirror up here. Then down, get directed down to the tertiary mirror, and then from the tertiary mirror they go right up here to the into the line of sight there off the high resolution telescope. And it's this very specific unique free mirror configuration. Minimal, allows it to take wide field views of the night sky, and usually with a telescope, one of the optical aberrations or abnormalities or nuisances, you get all these sort of funny optical effects out to the side. But with this extra configuration here, you minimise those. 8.4 metre primary mirror. The larger your primary mirror allows you to see higher resolution images of small, faint and distant objects. When you go into shop to buy your first telescope, don't let them blind you with magnifications and stuff, asking what size is that primary mirror, thank you very much, because that's what's going to give you your best views. So it's got a large primary mirror, and that's all in one there, and it's a secondary mirror. They're all relatively large sizes for what they are. The other amazing thing that makes it very unique is its camera. Check this out, 3,200 megapixel camera. Woo! Yeah, that's 3.2 gigapixel camera. So that gets the lights focused up from the primary mirror. So it's all those combination of things that makes it very, very special, whereby it's able to take in fact, I think I've put that up there, haven't I? It's, for you technical people, it's called a fast optical system, very short focal length, which gives it able to take quick snapshots in a very short space of time, really bright, high resolution images, very quick at wide fields. You know, that takes a very special camera to do that with that configuration. So let's have a little bit closer look at that. So its field of view is 3.5 degrees in diameter. To give you an idea, is the moon's diameter is about half of a degree. So it's a huge area of the night sky. It's one single exposure, 45 times the size of the full moon. So you imagine that, you see a full moon, 45 times the size of that. It does that in one quick snap, in a 15-second exposure. And it takes two 15-second exposures, 15 seconds over that wide field. High resolution, can pick up faint, distant objects. Then it slows very quickly, slows and refocus, moves on, refocus within 5 seconds. Next large patch of sky. High resolution, really picking up faint objects, 15 seconds, 5 seconds, bang, locks on again. Pretty incredible stuff. And what that enables, it scans the complete southern sky every 3 days. So it's in the Atacama Desert, so it looks at the southern sky, the best part of the Milky Way. 1,000 images per night. And of course, each time, every 3 days, when it goes back over that same part again, it's able to get gather more light, which the computers then stack up, so it's able to see further back in time and depth. Yeah, over 10 years, its mission is over 10 years. 825 complete scans of the sky, just doing that constant, that high resolution, wide field, minimal aberrations and so on. And it's called the Legacy Survey of Space and Time. Over that time, it hopes to be looking at 10 billion galaxies. 10 billion galaxies over 10 years, pretty amazing, and high resolution. This is another short little video here.
Oh, yeah.
What did I do wrong here? Okay, so let's try it manually. I think some of that. So what's happening here?
It's running. It's running.
Oh, you didn't do it yet?
Yeah, Martin. Yeah?
I've lost the video.
It's connected to the icon. You might need to force it to connect to the computer. We need to exit and then check the audio.
Oh, that's a shame. We can do that. We don't have to do the videos. The sound, we don't have to do the sound.
Alright, so this is a really cool opportunity. We actually get to see the Simony telescope, the LSST array, it's all moving. And what you're seeing right now is it moving slowly. It moves much faster than this. And remember we talked about the fact that this can shoot the entire southern sky in 3 nights. I mean, that is incredible. No other telescope can do that. And it's thanks to this powerful design and very interesting motors. And this is so significant because, look, there are other telescopes in the world that have similar fields of view, but nothing that can shoot at the relatively fast shutter speeds that it does, at the speed that it's able to traverse the sky, and how many photos it can take over time. I mean, that means that the dome moves quickly, the scope moves quickly, and all of this while everything's in focus and aligned perfectly. And so how do you move the world's largest camera and this giant telescopic array smoothly and quickly? Well, it's actually fluid dynamics. So they're actually pumping high pressure oil from below, and the array is floating on this oil. Now, I've been told it's not baby seal oil, it's not 5W40. I've been told it's synthetic and that's it, but it's pumped at extremely high pressure to the point where the array is actually so easy to turn that we've been told the petapixel team could actually by hand rotate this entire array. They're not going to let us do that, but 3 people can actually move this thing by hand. But the speed goes beyond just the actual physical movements of this telescope or how fast the camera can fire. It also comes down to how quickly they can transmit data. We're going to talk about that next. Okay, so I've been told that it's quite noisy here, and that's because we've got the data processing center right behind us here in this room. Now, all those images that come out of the camera, they're actually immediately sent from the back of that room directly to the SLAC laboratories in Stanford, where we first saw the LSST in our first video. Now, this is incredible because they have a fiber optic cable network going from here all the way to SLAC directly 103,000 kilometers. Now, these images, I said, are about 25 gigs. They're compressed down to, let's say, roughly 8 or 9 gigs and sent over the fiber optic network, and they arrive at the SLAC laboratories in less than 10 seconds. And this constant streaming of data is very important because they can only store the information here at most for like a month's worth, and then it's full. But the SLAC laboratories, way more storage to start to contain all this. Now, this information does actually have to be held for about 80 hours, and I know that has some consternation amongst the scientific community, but we've been waiting for a lot of this data for billions of years to come here. What is another 80 hours, right? I do want to mention, though, that alerts will be sent immediately. Within a matter of minutes, that will be sent out to the scientific community. And alerts can be anything like the brightness of this area changed dramatically, or an object that was here is no longer here, or this has moved a significant amount. We're talking about, I don't know, something like 10 million alerts every night. So there's still going to be tons of data released immediately. So the actual data throughput is fascinating. It takes these very loud computers to operate, but I can say, I mentioned scientists love photographs. And yes, James Webb, Hubble, they capture beautiful color imagery that just sparks the imagination of the public. But the Rubin Observatory can also make beautiful photographs. And what we're here to be a part of is to get to experience these first public images released. So let's take a look at them now.
Pretty amazing, isn't it? The high resolution. Each of those dots is an entire galaxy. There's millions of galaxies in there. Pretty amazing. This moving along. So they've had 4 core science missions: probing dark matter and dark energy, exploring the transient optical sky, which you talked about, you know, what things have changed the night before, cataloguing the solar system, and mapping the Milky Way. So here's your next question. What methods or method will you be used to study dark energy with the Vera Rubin telescope? A, baryonic acoustic isolations. 2, baryonic acoustic isolations to type 1a supernova. C, baryonic acoustic isolations, 1a supernova and spectroscopic galaxy redshifts. D, baryonic acoustic isolations and spectroscopic galaxy redshifts, just the 2 of them. Or E, baryonic acoustic isolations, type 1a supernova and photometric galaxy redshifts. So have a think about that for a minute. And, okay, who got E and hasn't had a chocolate before? Yeah. The whittling down. Everyone can get one at the end, isn't it? Okay. So the thing that probably caught you out was the difference between spectroscopic galaxy redshifts and photometric redshifts is probably the thing. Here's just another one too. What are the recent observatories are studying dark energy? I'll put this one in here. And look at all these different observatories, and the answer here is E, all of the above. My point of this slide was just to point out that this whole field of dark energy is just still unknown. It's so exciting. There's a lot of resources and observatories going into the studying of this dark energy. Why, you might say, why do they have all these telescopes? Each one will work optimally at different wavelengths, different methods. Of course, as we talked about before, different methods great for calibrating your data to, comparing one method, looking at the same thing, one method, looking at the same thing with another method. They have different approaches to it, some more looking at the universe, different time epochs and so on, or changing universe. So each of them is going to do their little bit towards a dark energy. We can talk more about these during next year, because they're all pretty exciting in their own right. Yep. Different methods, wavelengths, regions, and focus. Yeah, and there is combined results, calibrate and building up a complete picture of space and time combined to get a good grip on dark energy. So I just threw that in there. Okay, so we talked about baryonic acoustic isolations, and just a couple of slides I put in there from the monthly talk, just to recap. That refers to when you look into the sky, they see a statistical arrangement of galaxies, and there's lovely big circles, if you will. And they represent, way back in the early universe when it was just all thick plasma, there was compression waves going on with radiation pushing out, gravity pulling things back, and these compression or sound waves, and they created these little circular arrangements of matter. And then as the universe cooled down, these circular arrangements of matter had left an imprint, and you see it today by looking at the galaxy with these circular arrangements. And they're able to measure this from the centre of these circular arrangements out to the outer regions of the circle there, each one, and that gives them an idea of how the universe expanded. So you look at different epochs, different times back at different stages of the universes, and look for these circular arrangements, measure how big they are, and that will give you an idea how the universe has expanded over time. So that's that one there. Type 1a supernova, you're probably familiar with those. They refer to a specific type of the most brightest form of explosion from stars exploding, and that's when a red dwarf is in a binary system, a white dwarf is in a binary system with a red giant. Material siphons onto its hot surface until you get a critical stage where you get nuclear fusion going and the whole thing blows up. So that's that. But the other one I really want to talk about is photometric redshift measurement. You're probably familiar with the spectroscopic redshift, whereby there's absorption lines on the spectrum that at certain positions, certain wavelengths for certain elements and so on. But if you see they're all shifted towards the red end, and we talked about this during the talk, you can have a look online if need be, and you see that they've all been moved over to the redder end of the spectrum, so that's called spectroscopic redshift. But there's another way called photometric redshift measurements that the Vera Rubin uses, and it's more ideal for these big all-sky surveys, and whereby a galaxy, its big, bright, hot stars are blazing away in light right across the spectrum, in particular intense ultraviolet light, and neutral hydrogen that's within that galaxy and between us and that galaxy is quite busy absorbing ultraviolet light at wavelengths of about 912 angstroms. So you would naturally see the brightness looking at that galaxy through different filters, and they usually have 6 filters. I think they've got in this example 5, but the Vera Rubin's got 6, but filters in different bands at specific bands of size of wavelengths. And they measure the brightness, and here it is here, the brightness, and you see it, suddenly the brightness drops off. And it usually, if the galaxy was very close to us, it would drop off at about 912 angstroms. But of course, the further something is away further, that's called the Lyman, because of the Lyman series of ultraviolet light. It's called the Lyman break, and you suddenly get a break or a drop off in the intensity when you're looking through different filters. And it just gives you a crude but accurate enough estimation. So the further a galaxy away is, that Lyman break or that drop off is no longer in the ultraviolet. That now drop off is way in the near infrared and optical wavelengths. So you'd see this drop off here happen a lot quicker. And so they use that's called the photometric. So I threw that in on purpose for the redshift in galaxies. There are two ways you can actually look for the redshift in galaxies. And of course the redshift refers to its distance away from us. Okay, now the other one was what objects will be studied as part of mapping the Milky Way? A, solar flares. B, stellar streams. C, brown dwarfs. D, B and C, or E, all of the above. Of course, the answer is E, all of the above. Yeah. So, who got that right? They didn't get hasn't had a chocolate. No, I think we've got. So there'll be chocolate for everyone as you leave. So that's all good. We're all good there. Okay. Now the idea behind here is to detect really faint objects if they can, to get a better picture, build up the picture of the Milky Way. Brown dwarfs, other faint objects, variable stars, that the Gaia telescope's already picked up, get an accurate thing of their distance. But I think I'd pick on here, so you might say, what are stellar streams? And the idea behind stellar streams is that you've got the Milky Way here, a reasonable sized galaxy. Smaller satellite galaxies get attracted through gravity with it, and they get absorbed by the Milky Way. They don't just come in and collide like that. They're coming in at different angles, and they do a bit of a sweep, a bit of a dance. And when they do that, the tidal forces just doesn't absorb it. It starts stretching out. The gravitational forces of the Milky Way between the two stretches it out into these nice thin streams. And slowly they go round and around the Milky Way and slowly get absorbed every time they sort of make a pass of the Milky Way. And so it follows there that if you're able to analyse with high resolution the motion of each, identify those streams, but identify the motion of these stars all travelling together. You think, well, that's a group there, that's a group there, they're part of that stream. Look at their chemical composition, you'll get an idea of their age, but also your computers will count backwards, they're supercomputers, and actually do a model of where and when those galaxies collided, first made contact with the Milky Way, and from there you're able to work out the evolution of the Milky Way, how the Milky Way was slowly built up, where, how and when it was built up to what it is. So this is just one of the many things that the Vera Rubin telescope will be doing. Pretty amazing stuff. And that's okay. The Gaia Observatory, that's just been retired. It was launched a European high-resolution telescope, just identifying stars and distances to them and stuff. And that identified 3 of these streams you can see there. Okay, moving along now, spectroscopy. We talked about how light can be split up by grating or with a prism into all its different separate wavelengths. So looking at stars, what stellar properties can spectroscopy observe? Surface temperature composition, radial velocity and rotation rate, surface gravity and magnetic fields, or all of the above, or you forgot. Okay. It's all of the above, yeah. It's pretty amazing what they can tell. I think from just analysing, splitting up the light from stars, you can tell the surface temperature. We went into quite a bit of depth and we went through the equations of working out the temperature of our sun. But these here, this is called an energy, a spectral energy distribution curve, and you've got the flux, how much energy here, across here you've got your wavelengths, and typically through your spectroscope you get these nice, with increasing intensity up to a point, then it goes back down, and you get these dips, and that's where light from the star has gone through its atmosphere and then carried on to us. And whatever elements and what sort of energy states they are in the atmosphere of that star absorbs that light coming through, and when we observe it we get a dip in the intensity which come across these called absorption lines. So more details about that in the monthly talk. That's just a basic rundown. So I've pulled out a couple of things here. One is the rotation of the star. So you can actually, through analysing its light, you can work out its rotation rate, how fast it's rotating around. And the idea behind here, let's say if that was a non-rotating star, every star does rotate, we just say, give a nice absorption line there. But if it's rotating, because of the Doppler effect, and the Doppler effect, as we talked about, where light travelling towards us in waves and wavelengths, light gets squashed up, if you will, so it appears at the bluer, shorter wavelength end of the spectrum. Light travelling coming to us from an object that's moving away from us, in this case light from this end of the star that's travelling away, the star's rotating that way, the light gets stretched out into longer wavelengths or redshifted. And because of that, the absorption lines get a little bit widened and broader. And it's the amount of broadening indicates the rate of rotation. So not only can you tell the temperature of a star looking at it, you can tell how fast it's rotating. And you can tell its surface gravity. You might think, why do you want to know the surface gravity, what it's like? That tells you how compact a star is. For example, you might have two stars in the same spectral class. Let's just say M class spectral classes. And you want to know, is that a red giant, or is that a maybe more compact, say a main sequence star? And here, for example, blue is a more compact star, and the green is no, actually that should be green. Yeah. But anyway, you can see the green is a less compact one, but the spectrum is exactly the same. But when you analyse it at high resolution, look what you can see. The more compact one, see that the spectral line up close is actually a lot broader than say the green one. And that is because a more compact object, the gravity is stronger, so gravity is pulling its atmosphere down. So its atmosphere is more dense, it's more active, there's more collisions going on, and so on. More energy levels, more electron transitions going on, and you get a wider range of energy levels going on, of photon energies. So you get these broader lines here. So that is very useful to astronomers. Okay, that's what we've just talked about. Okay, now looking at spectroscopy at these exoplanets. So we've looked at stars, what its host star, and that's how you can tell what a host star and information is from spectroscopy. How about now if you're looking at the atmosphere, or looking for an atmosphere, and you see an atmosphere around an exoplanet? What exoplanets, what molecules in there serve primarily as biosignatures of life, and a biosignature means a chemical that indicates that there's life, there's quite possibility of life there. A, oxygen and methane. B, oxygen, water and methane. C, oxygen, methane, dimethyl sulfide or phosphine, or all of the above.
D.
Well, yeah, I will give you D, but the answer actually is C. And the logic being, there's a little bit of trick, so you allow D, but the logic here is that water is one of the conditions of life, but water can exist quite happily without life. Water itself is a good thing to look, it's a damn good start. If you haven't got water, you better to move on and find one that does have water, but it's not a biosignature of life. Of course, these chemicals here are all produced by microbes on Earth. So let's just talk briefly about the James Webb that's been looking at, and there's a lot more powerful telescopes that are coming out in the future to do better jobs of this. But the idea here, instead of light shining from a star going through its atmosphere being absorbed by individual atoms, you've got light from the host star that's shining through. You've got your exoplanet here, thin atmosphere, and the light from the host star goes through the atmosphere. You analyse it here, but as the light passes through the atmosphere of that exoplanet, it gets absorbed by molecules in that atmosphere, molecules that start vibrating and rotating at very specific wavelengths. And it's that shows your absorption lines, but very broad ones at that. And the absorption lines are very broad because suddenly you might have atmosphere. If you've got an atmosphere, you've got winds and so on. A lot of them, molecules bumping into one another. So they're very broad. They're not exact. We talk about that in the talk as well. Try to decipher the data. But what to look for? What are these biosignatures? Your oxygen, O3 definitely means life. Small amounts of oxygen can get produced by abiotic means. Methane, once again, can be produced by geological processes but life. But if you get both of them have very short half-lives, don't hang around in an atmosphere for long. So if you get both a decent amount of oxygen in combination with methane, that's highly suggestive of life. Water vapour, as I put the asterisk there, that is, you certainly gets your interest, but it's not a biosignature as such. Nitrous oxide, organic compound sulfurs, and phosphate, they are all produced on Earth, as far as we're aware of, only produced by microorganisms. Having said that, the dimethyl sulfide and dimethyl disulfide have been found on comet, I think it was comet P67. How did that get there? We don't know. So obviously we've got to know a bit more. But for now, and of course, chlorofluorocarbons, if you see those, obviously that's got to be produced by industry. You've got civilizations, pretty dumb civilizations, admittedly, because they're destroying their own atmosphere, which we're pretty good at. So, but that means you've got arguably advanced civilizations there. Okay, moving on now, very much time-wise. Let's move on to the moon. Apollo moon landings. Okay, what mission is this taken from? Any takers on that? What mission is this taken from? No. 14. No. It's Apollo 16. That's national. That's John Young, very famous. We talked about that. That's him doing his jump for joy, and that's an ultraviolet spectrograph sitting behind him there in the shade, so doing some good science. So that's Apollo 16, John Young. What do the red stripes on his suit represent? Yeah, he's the commander. Why did they do that? Because the early missions, they looked at the photographs and realised, oh, we can't tell who's who here. So they put they thought we'll make the commander feel extra special and give them some red stripes. So they did that. So what missions onward were they introduced? And there's actually two answers there. Okay, they were introduced after 11 and 12 for 13, but 13, of course, didn't get to be worn on the moon. So on the moon, it was Apollo 14 were the first guys to have the commander with the red stripes. Apollo 14, but they actually were introduced to Apollo 13. A little bit of trivia. What mission landed in the Sea of Tranquility? Yeah, Apollo 11, yep. What mission landed in the Taurus-Littrow region? High up in the highlands between some big valleys and stuff. That was Apollo 17. What mission hiked, and there's a clue there, hiked to Cone Crater? 14, yeah. The clue there is hiked. They had that long walk, they had a cart that they carried all their equipment with. So 11 and 12 just walked, 14 had their cart, and then the rover came in. Next, what mission visited Plum Crater? 16, someone said 16 over there, yeah. Apollo 16, that's right. Did you get a chocolate before? You didn't? Oh, you need one, yeah. Apollo 16, up in the Descartes Highlands, yeah. Famous picture there of, that picture there, of Charlie Drake. There's Charlie Drake next to Plum Crater. That's a very famous picture there. Okay, yeah, what mission was the first to use the lunar rover? We've already answered that. 15, yeah.
You got chocolate?
Yes. Go on, man. Watch out for pimples. So yes, there it is there. That was a huge jump forward. Electric motors on all four wheels. Top speed, 18 kilometres per hour. It was, how far could they go? And it was constrained by the oxygen supply to the astronauts. There's no point going for a drive yonder, it breaking down, and it's going to take you 4 hours to walk back and you only got 2 hours of oxygen. Not a good look. So they were constrained. They could have gone further, but they were constrained by how much oxygen they had left, should they have to walk back. So yeah, it increased the productivity of geology. It's huge. Okay, here's a little video of it. It's quite cool.
Deck on, board. Max acceleration.
You see it bouncing, low gravity. Yes, they talk about rooster tails.
Man, you are really bouncing.
That's these tails of dust flying up. Look, see, there it is, behind the wheels. It's low gravity and no atmosphere.
He's got about 2 wheels on the ground. It's a big rooster tail out of all 4 wheels. And as he turns, he skids, the back end breaks loose just like on snow. Come on back, John. And the deck is running. Man, I'll tell you, Andy's never seen a driver like this. Okay, when he hits the craters and starts bouncing, and when he hits his rooster tail, he makes sharp turns. Hey, that was a good stop. Those wheels just locked. Mark off.
Yeah, there you go. So that was the lunar rover. Let's move on for lunar science. We'll finish up now with lunar science. That was, by the way, Jack Schmidt from Apollo 17. So what surface experiment is Buzz Aldrin setting up here?
Solar winds?
Yeah, the solar wind. And what 2 prime particles is he collecting with that solar wind experiment? Coming from the solar wind. What's the 2 commonest subatomic? Yeah, there was a little bit of alpha particles. What are the 2 commonest subatomic particles? Protons and electrons. Yeah. Protons and electrons. So that was a very thin aluminium foil. They put it out. 90 in sort of the subatomic particle got embedded in it from the solar wind. 95% of it, not unexpected, is protons and electrons, plus a little bit of your helium nuclei there, which is your alpha particles. And at the end of their moonwalk, they then roll that up and take it back to Earth to get it analysed. Okay, so the surface experiments, there were 6 main surface experiments. A seismometer that measured a seismological activity on the surface of the moon, little moonquakes from tidal forces on Earth, asteroids and meteorites and so on striking the surface of the moon. And of course, you could help determine the internal structure of the moon. So they crashed the ascent stage of the lunar module and some of the 3rd stage of the Saturn V rocket. They purposely, deliberately crashed them onto various parts of the moon just to set up vibrations on the moon that they could then monitor and check out to help them deduce the internal structure of the moon. Magnometer, checking out the strength, magnetic fields on the moon, different places and the strengths of them. Heat flow detectors, trying to detect any heat, a little bit of minimal amount of heat coming up. They thought that's from the interior. The conclusion was the moon essentially is geological activity, notwithstanding tidal effects with, as I speak that from the effects from the Earth. Laser Ranger, that's that thing here that they still use today. Astronomers point laser beams at it and it bounces back again, and they can determine the exact distance from the Earth to the moon, confirming the calculations that the moon is moving 3.8 centimetres every year away from the Earth, as they thought it should be. Physics, atmospheric composition. The moon doesn't have an atmosphere to speak of, but technically it's got a very subtle atmosphere. They're able to analyse that, and the solar wind experiment. Because of course we can't examine the solar wind on Earth because of our atmosphere, so there's no better place than a nice stable platform on the moon to do that. We talked about that in depth. How much rock in total did the astronauts bring back? That's from all the 6 landings. 250, 282, 350, 382 or 450 kilograms? 382, yeah. Anyone get that who hasn't had a chocolate? No? I think everyone's had a chocolate.
I got it though.
Yeah, that's good. Yeah, 382 kilograms. And 110 of those, so that's just under a third of it, was brought back by Apollo 17. And that was one of my main threads or themes of those Apollo moon landing talks, where each mission got successively more and more, did more science, spent longer on the moon, brought back moon rocks and so on. And it just went up exponentially. The graphs just went like that as they got better and better at it and brought more back. Okay, what are the 3 types of moon rock? Just have a think about that. Yeah, so who thought of basalt? Yeah, basalt and orthosite and breccia. They are your 3 main forms of types of moon rocks. Your basalt is it's heavier, it's got your magnesium and iron in it, so it looks darker, and it is responsible for these darker mare. And these mare were formed where the surface of the moon was covered with a crust, and the crust is predominantly orthosites, which are very pale, made predominantly of the pale and light elements like calcium and aluminium and the likes. So that formed the crust. Then you had these massive impacts, these massive big asteroids and stuff striking the surface of the moon, digging in deep, causing little fractures, and the heavier, dark molten lava would come up and as basalt and flood the big basins and craters to form these dark maria. And of course, all the material excavated, the crust excavated, formed these big white highlands around here, which is your anorthosite, which would have been the original pristine crust of the moon. And breccia is really, around the sites of impacts, is sort of fragments, multiple fragments of multiple different types of rocks that have been smashed and cemented together, and they're indication of impacts. And it was Apollo 16 when they went up to the highland craters to the Descartes Highland region there, and they looked at Plum Crater because they thought this area looks very volcanic in origin for these craters. But all they found, like around all the other craters, there's a lot of breccia, indicating that almost all the craters on the moon are impact in nature, not volcanic in nature. Okay, and I think that's the end of the quiz at that time. So thank you for coming along, and hope you have a safe and happy holidays. Drive home safely. Thank you. There we go. We'll see you in a week's time. We're all good.
Good to see you a lot longer.